Good evening, everyone. Now we are going to start the class. Right. So last time we discussed after the compressibility factor. Now today we have to start from the Van der Waals equation. Okay, that was the thing that we were discussing. Right. Van der Waals equation means now when we talk about the ideal gas equation and other equations that we were learning last week, now those can be applied for only the ideal gases. Those can be applied for last week. Boyle or Charles law Avogadro applied for ideal gases. Is it clear? That means it's not fair to use those equations for the real gases. What are the real gases and what are the ideal gases? No, almost all the gases around us are real gases because they have real existence. Ideal gases means the gases with zero intermolecular interactions and do not occupy any volume in the free space. Are there real gases like that? Without intermolecular interactions and does not occupy any volume? No. That means all the gases around us are real gases. Ideal gas is just a concept. Got it? Ideal gas is just a concept. That means it's a conceptual, not ideal gas. Then for the real gases, we have to apply those equations. So it's not fair to apply the equation as itself. Why? What is the reason? Because the real gases, they do not behave ideally. Therefore, when using the ideal gas equation and other equations for the real gases, we have to do some corrections to those equations. Especially we are doing a pressure correction and a volume correction. The pressure correction and the volume correction is done. Is it clear? Right. So those are the things that we are going to learn under this Van der Waals equation. Actually, that correction was done by the scientist. His name was J.D. Van der Waals. J.D. Van der Waals, he was a scientist who made the corrections. Right. Now we know that the equation of state, that is PV equals nRT, it's not fair to use that as it is. Right. You can write the topic today. Van der Waals equation. Van der Waals equation. Not down. Yeah. Is the part of his name or name his name? It's not no, his name is J.D. Van der Waals. That's his name. Not apostrophe. Then if there's apostrophe Van der Waals game, that's a direct matter. It's not like that. That's Van der Waals equation, like Boyle equation, Charles equation. Even Charles is his name. Charles, that's his name, not Charles. Like this. You can note down. In order to understand the behavior of gases, we use the equation of state. In order to understand the behavior of gases, we use the equation of state at the beginning of this lesson. Equation of state at the beginning of this lesson. But it's not fair to use the equation of state as it is. It's not fair to use the equation of state as it is for the real gases that we meet. That is because the real gases show a deviation from the ideal behavior. Real gases show a deviation from the ideal behavior. Is a new point. In order to overcome this issue, J.D. van der Waals a Dutch physicist. So that's why his name is also, it's not English. J.D. van der Waals proposed a new equation. By applying a pressure correction and a volume correction. A pressure correction and a volume correction. Right. And you can write down the pressure in a real gas. The pressure in a real gas is lower than the pressure in an ideal gas. Because there are intermolecular forces. Between the gas molecules. There are intermolecular forces between the gas molecules, and they will lower the pressure. Therefore, when applying the pressure for real gases, we have to apply the pressure correction. We have to apply the pressure correction. Now we know that ideal gas pressure is greater than the real gas pressure. Why is that? Because due to the intermolecular forces between the gas molecules, the pressure in a real gas is been lowered, it's been reduced. Again, ideal gases, so there are not any intermolecular attractions. They are the pressure in real gases, due to the intermolecular attractions between the gas molecules. Okay, now first of all, tell me how the pressure is exerted. Sorry. Yeah, that means we have a container, the gas molecules, they move at high speeds and hit the wall. So once they hit on the wall, that force creates a pressure on the wall. Initially, if the gas molecules are not having any interactions with each other, these gas molecules can hit the wall with some force. That is the pressure, that is called the ideal pressure. Then if there are intermolecular forces between the gas molecules, what will happen? The force that hits the wall is lesser. Why? These gas molecules are confined to each, so it's not free to move as in the ideal case. Is it clear? Since there are intermolecular forces between the gas molecules, they are not easy to move. Freely අටපුලුවන් එක කවුරු හරි අල්ලන්නේ. Then you have to express like that. Because I see their facial expression. If they understand something, yes, I can see from their faces. And I cannot see it from your face. If you can't use the facial expression, then just steal it from your mouth. Then otherwise I'll be repeating the same thing for so therefore the ideal gas pressure is greater than the real gas pressure. Then to equalize the ideal gas pressure, we have to add some pressure correction to the real gas. Right now we know that due to the intermolecular attractions, some pressure has been reduced. So if that reduced pressure has if the amount of pressure reduced is added to the real gas pressure, then it will be equal to the ideal gas pressure. Got it? Right. So that pressure correction is applied. That is A L squared over V squared. Then this is equal to ideal gas pressure. So A squared over V squared, that is the pressure correction that we apply. Is it clear? Right. You can write this one, pressure correction. Right. Then that is the pressure correction. Then there should be a volume correction answer. Volume. We try to see those things and should be that's a good I should go in there. Nice. Yes. Right, so that is the pressure correction. Okay. Then volume correction. Next one. You can say you can note down at high pressure. At high pressure, the repulsive forces are significant. At high pressure, the repulsive forces are significant. Since the molecules are almost in contact with each other. As a result, the repulsive forces cause the molecules to behave as small spheres. Cause the molecules to behave as small spheres. Then you can say behave as small spheres. Then the ideal volume should be less than that of measured volume. Then the ideal volume should be less than the measured volume. Because a significant volume has been occupied by the gas molecules. So the ideal volume, now it is lesser than that of the real volume. So it equals to real volume minus ND. That is the volume correction made by Van der Waals. Ideal volume equals to real volume minus ND. You can write it. Then you can say, having taken into account the pressure correction and the volume correction, having taken into account the pressure correction and the volume correction, we can rewrite the equation of state. We can rewrite the equation of state as follows. So we can combine these together and we can rewrite. Right. So this is the Van der Waals equation after the correction. Right. So after making the correction, we can write it like this, Van der Waals equation. Right? Exactly. Right. Did you write the Van der Waals equation? Like below this, you can say this is the Van der Waals equation. This is the Van der Waals equation. Right. Now let's learn the parameters that we are used over here. Right. A and B are called the Van der Waals constants. Right. So did you write that this is the Van der Waals equation? Okay, this is the Van der Waals equation. Right. So we can say A and B are Van der Waals constants. Right. Simple N is the numbers of moles and B is the volume. Right. So A and B are Van der Waals constant. Usually, those are being given with respect to the gas. Actually, you don't need to remember those values. Even I can't. Then you can say, now this is the common equation. After that, we can write down. If we write this equation, so if we write the Van der Waals equation, if we write Van der Waals equation, for 1 mole of a gas, for 1 mole of a gas, it can be given as right. So we can remove all the m's because n is 1. So this is for 1 mole of a gas. Right. That is for 1 mole of a gas. Finish. That is regarding the Van der Waals equation. Right. So now we are going to start the last part of this lesson. That is regarding the critical temperature and the liquefaction of the gases. Right. You can write the topic. The critical temperature and liquefaction of gas. Here we have. Again, it's the same as ideal gas equation. The only thing is we have to do these corrections. Because for example, we have to substitute it. That's it. In fact, for the exam, they are not asking the calculations from the advanced equation. Always we assume the ideal behavior, we can find the values using ideal gas equations. Right. So to write the topic, critical temperature and the liquefaction of gases. That is the topic. Critical temperature and liquefaction of gases. Right. Now we know that once the gases are compressed, with a high pressure and their temperature is lowered, what will happen? They will be converted into liquids. Yes, that process is called liquefaction. Liquefaction. This one. Is it my fault? Which was the right, okay. So it's like this. If we take a gas and we cool it and we compress, if we lower the temperature of the gas and we apply a high pressure to compress it, the gas will be converted into a liquid. If we further decrease the temperature and increase the pressure, the liquid will convert into a solid. So those are the three phases of matter. Three states of matter: solid, liquid, and gas. That means by changing the temperature and the pressure, we can make what? We can make an interconversion between the matter. No? The matter, in between the matter, we can make an interconversion by changing the temperature and pressure. So, if we increase the pressure and decrease the temperature, gases convert into liquids and liquids into solids. If we decrease the pressure and increase the temperature, solids convert into liquids and liquids into gases. That means that process is an interconversion between the states of matter. Right. Now, here I am talking about the temperature that is called critical temperature. So, critical temperature is the temperature where the vapor of a substance cannot be liquefied. How much a pressure is applied? Why? So there's a why not? I'll explain. Right. So that means there's a temperature called critical temperature for a given substance. Right. At the temperatures above critical temperature or at the critical temperature, a gas cannot be liquefied. How much the pressure is applied? Sorry? It's a kind of optimum temperature. We call it the critical temperature. And there's a critical point. Can critical point again එහාට රන් කරාම නේද? කොච්චර ප්‍රෙෂර් වැඩි කරාත් ඒක අපිට ලික්විඩ් එකක් කරගන්න බෑ gas. That's the thing. That's a limiting. Yeah. Okay. So let's learn about this one. You can write it. The critical temperature of a substance the critical temperature of a substance is defined as the critical temperature of a substance is defined as the temperature defined as the temperature at and above temperature at and above which the vapor the temperature at and above which the vapor of a substance cannot be liquefied. Vapor of a substance cannot be liquefied. No matter how much pressure is applied. No matter how much pressure is applied. Right, so that is called the critical temperature. Right. Then let's say the critical pressure of a substance. Next one, the critical pressure of a substance is the pressure required. The critical pressure of a substance is the pressure required to liquefy a vapor. To liquefy a vapor at critical temperature. Right. For example, let's consider like this. For example, let's consider the interconversion between the interconversion between the physical states of carbon dioxide, CO2. Interconversion between the physical states of carbon dioxide. Right. So it's like this. Right. So as the y-axis we consider the pressure, as the x-axis we consider the temperature. Pressure and temperature. Excuse me. Right. Temperature is in degrees Celsius. Let's consider pressure in atm. Right. Those are the units. Right. So if we consider the phase diagram of carbon dioxide, what are the three phases we know? Yeah, solids, liquids, and gas. No? Right. So let's see how those phases will vary. So it will increase like this. Yes. Yes, that's what I'm going to explain now. The bulk liquid forming is here on that. Definition again, no. We'll see. Right. Celsius, we are considering Celsius and 18. Yes. So this phase diagram is given based on the ATM and Celsius. So Kelvin करो तो ना कोटा कितना टाइम है? अरे कर रहा Right. So the diagram is like this, huh? It is somewhat closer to straight line. Give me a second. Draw this one. I think now leave it on this one. I like pen first, then I give you enough time to draw it. Okay, now the shape of the phase diagram. Now what they are doing, I am not explaining second time. So this is the phase diagram. So this point is called the critical point. I name it as capital T, and this point is the critical point. T is the critical point. And C is the critical point. The temperature corresponding to the critical point is called the critical temperature. So this temperature is called the critical temperature. For carbon dioxide, that value is 30.98. Then the pressure corresponding to critical pressure is called critical point is called the critical pressure. For carbon dioxide, that is 70 7380. So that means this is the critical point. According to our explanation regarding the critical temperature, this is the temperature, right? This is the critical temperature at which or above where the gases cannot be liquefied again. That's why this will stop over here because this is the vapor phase. And this is the liquid phase. And this part is a solid. Right. Solid, liquid, and vapor. Now we know that, see, at high pressures and low temperatures, substances stay as solids. At high temperatures and low pressures, they will exist as gases. No? The pressure is less. See, pressure is less, and the temperature is high. So therefore, they are vapors. So we can compress and liquefy this vapor into liquid only up to the critical point. The critical point taking see the curve stops over here. That means we cannot liquefy that gas further into the liquid, vapor into the liquid. Did you understand? The beach. Right. So then what happens means? So if it increases, then it exists here. Critical point in gases is nothing.
So the incremental critical point for the temperature or is related to pressure?
Temperature. So you get almost critical temperature. The pressure corresponds to critical temperature is critical pressure. That means see, at critical temperature, if we apply the critical pressure only, that vapor is being liquefied. That means if we apply a lesser pressure than the critical pressure, it won't be liquefied. Right. So here, the triple point is there. This is also important point. Triple point is the point where the solid, liquid, and gas, all three phases are in equilibrium with each other. Solid, liquid, and gas, all three are in equilibrium at the critical point. Sorry, at the triple point. So that pressure is 5.11 atm and the temperature is minus 56.4. Now this is the well-known pressure, that is 1 atm, that is room temperature, atmospheric pressure. Right. There, the temperature will be minus 78.5. All right. Now, if we consider this carbon dioxide gas, now here there is an interconversion between solid and liquid. Solid to liquid and liquid to solid. That will happen under these conditions. Here, liquid into vapor and vapor into liquid. Interconversion is across this curve. Here, solid to gas and gas to solid as well. Right. Now we know that carbon dioxide exists at room temperature as a solid, liquid, or gas. Yes, carbon dioxide is a gas because at under atmospheric conditions there is 1 atm. And what will be the room temperature? Now it is 36. These days it goes more than 30. Not in this room, outside. In this room, it's about 25. Since it is air conditioned. Okay. So in the normal atmosphere, the temperature is about more than 25. So 25 temperature is over here. See, this is the temperature curve. In the temperature axis, the temperature 25 is over here. So at that temperature, if we consider 180 atm pressure, so what will be the phase? Vapor, that means gas. So carbon dioxide exists naturally as a gas. If we cool it, what will happen? At 180 atm, at 180 atm pressure, if we cool it, now the temperature is decreasing like this. If it decreases up to minus 78.5, the gas starts to solidify. So once it is solidified, we call it solid carbon dioxide, we call it dry ice. Do you know that dry ice is there? Yeah, dry ice is there. So if we increase the temperature a bit above 78.5 minus 78.5, the solid directly converts into gas. Is it clear? Not to liquid, it's into gas. Right. Conversion of solid into liquid takes place more than 5.11 atm pressure and minus 56.4 degrees Celsius. See, එතනින් තමයි solid liquid වෙන්නේ. අපි temperature වැඩි කරද්දී. Is it clear? Even if we decrease the pressure, then it will become a vapor. Got it? That means the minimum pressure required to form liquid carbon dioxide is 5.11 atm. Below 5.11 atm, there are no any liquids. Is it clear? So those are the phase diagrams. Don't get panicked because this is just the introduction of the phase diagrams. We will be discussing regarding the phase diagrams further in the topic number 12. Under phase equilibrium, we are talking about this one a bit, and we will be discussing in detail about this in the university. I know you are not going to teach, you are not going to learn chemistry in university, so then you are safe. Okay. Yes. Okay, you can copy this down. Huh? Copy this down quickly.
Okay, we have my chemistry PG. 100% taking up the system on the same and we are looking forward to it. Moment air got you teacher. No, she was. Now she was. Even after that, done it. Baja is really fun. It's good, man. I missed it last. Never buy that.
Good. And during this time. No, this was on her version. That was on her. Pictures. So for your temperature, 1 minute.
Easier to make it. I got a which will be I will be a lot of benefits. So then let's move on. Yeah, same we have finished drawing this one. Finished? Okay, I'll give you another couple of minutes quickly. Right, finish. Below the diagram, you can write down phase diagram of carbon dioxide. So this is the phase diagram of carbon dioxide. Phase diagram of carbon dioxide. Now, did I give the rendering stage? Okay, we don't need this tube today, but we'll be starting the lesson. The questions are there in the tube. You have to bring it next week. I know none of you has what it is. I would say because it was aesthetics I had I want to say because it was right, so that's all. So let's see the question and let's do a question and then let's move on to the next unit, that is analysis. There is none of you have attended the data class last time. We'll be doing this question. Anna, you can do it as a homework. I'll give you another question. I'll give you a different question. Really hard was struggling. This question is the classic. I have pictures from those.
Ladies and features. You will understand now after this discussion. Right. So let's move on to this question. Right. You can note down this question. Consider the following diagram. Consider the following diagrams. Okay. Now there's a system made up of three bulbs X, Y, and Z. So this is bulb X, this is Y, and this is Z, and they are closed with valves. Okay, these connections are closed with valves initially. In next we have helium, 40 moles of helium at 6 into 10 to the power 4 newtons per square meter pressure. 40 moles of helium are there at 6 into 10 to the power 4 newtons per square meter pressure. The volume will be 1.6628 cubic meters. The volume of the bulb is 1.6628 cubic meters. Then there's bulb Y. It contains nitrogen at the pressure of 2 into 10 to the power 4. This is the valve P. Then there the volume is 8.314 cubic meters and it is at the temperature of 400 K. So if we consider the bulb itself, it contains argon gas, 200 grams of argon gas. grams are not moles. Volume is 41.57 cubic decimeters and the temperature is 300 Kelvin. Yes, 300 Kelvin. This is the valve Q and this is the valve R. So this is the system. Right, draw it quickly. There is another question. The diagram shows the piston composed of three bulbs. The diagram shows the system composed of three bulbs. Composed of three bulbs, X, Y, and Z. Which contain helium, nitrogen, and argon. The valves P, Q, and R are closed initially. The valves are closed initially. Then answer the following questions in SI units. First question. What is the temperature of bulb X? In part B. What is the mass of nitrogen in bulb 1? What is the mass of nitrogen in bulb 1? Then part C. Calculate the pressure in bulb Z. Let me find your answer. Right, so let's see how this question is made. Let's solve this one. Right now, it says the diagram shows a system that composed of three bulbs X, Y, and Z, which contain helium, nitrogen, and argon. The values P, Q, and R are closed initially. Sorry, the values P, Q, and R are closed initially. Answer the following questions in SI units. What is the temperature of the bulb X? So this is bulb X. Initially, the values P and Q are closed. That means this is only one system. Then two gas, helium. We can assume the ideal behavior of helium, and then we can apply this equation. We can say assuming the ideal behavior of helium we can apply PV equals NR. We are going to apply PV equals NR. Right. The pressure inside this one is 16 to 10 to the power 4 newtons per square meter. That means pascals. 1 Newton per square meter is Pascal. Then the volume is 1.6628 cubic meters equals to nRT. N is the numbers of moles, that is 40. And R is 8.314 joules per moles per Kelvin. And the temperature is one temperature thing that we need to find out. So then we can simplify. Temperature equals 6 into 10 to the power 4 into 1.6628 divided by 40 into 8.314. Now see, these are very easily simplified. Right. 8.314 into 2, what's the value? 16.228. Then can't you see a relationship? Which is 10 times that is not. That means we can cancel off those two together. Right. 1.6628 times 5 is 8.314. Remember these values. Now you always they are giving the values like this. It's times 5. Then that is 6 into 10 to the power 4 divided by 200. Two zeros are cancelled off. 600 divided by 2, answer is 300 Kelvin. Isn't that easy?
We can make it decimal to this side. And they will take one to one. Usually, it's also the same.
Yeah. That's good, but it's unnecessary here. But here it is unnecessary. Right, so instead of doing that, we can put the decimal over here, then it will become 16.628. Then 1 0 will be cancelled off. Then 8.314 times 2 is there. Then 2 times 1 becomes 20. Then 6,000 divided by 20, again the same answer to 300. Anyhow, these simplifications are easy. Then what is the mass of nitrogen in the valve Y? Now here we have valve Y. Okay, these values are given. Pressure, universal gas constant we know, volume and the temperature are given. Then for the valve Y, we can assume the ideal gas behavior of nitrogen. We can say assuming the ideal behavior of nitrogen gas. Again, we can apply PV equals nRT. Now you are supposed to find the mass of N. Right. Then we can rearrange this equation as PV equals numbers of moles equals to mass divided by molar mass into RT. Then we can subtract mass PVM divided by RT. Or else you can just apply the values and find mass. Anyhow, I'll be using this method. It's easy. Then the mass equals to pressure, that is 2 into 10 to the power 4 pascals into volume, it is given as 8.314 cubic meters, and the molar mass of nitrogen is 28 grams per mole. Then it has to be 28 into 10 to the power minus 3 kilograms per mole. Because the SI unit of mass is kilograms. Divide by RT. R is 8.314 joules per mass per Kelvin. T is 400 Kelvin. Then we can easily cancel off 8.31 to 8.314. Right. Then two zeros are here. We can cancel off the two zeros over here. Then it will become 10 to the power 2. Then 2 to the power 1, 2 to the power 2. Then 2 to the power 1, 2 to the power 14. Or else we can cancel off 4 and 7 over here. Because 4 times 7 is 28. Right. Then answer will be 40 into okay, 10 to the power 2 is 10 to the power minus 3. Cancel. No. Then answer will be 1.4 kilograms. Is it correct? Yeah, much better. Let me see. You can see this is 200 divided by 20.
Especially mine is 300.1 into base side.
Right, so 1.4 kilograms is the mass. Then RC, calculate the pressure in the bulb is it. I'm guessing this part. Huh?
So is it necessary for kilogram per mole?
Yes. Otherwise, you can apply grams per mole. Then we have to convert the final answer to kilograms. All right. Then the last one is calculate the pressure in the bulb is it. Yeah. Then assuming the ideal behavior of argon gas. Assuming the ideal behavior of gas. Ideal behavior of argon. We can apply P equals nRT. Right. So calculate the pressure in the bulb is it. Then pressure we don't know, that's the thing that we need to find out. Volume is 41.57 cubic decimeters, therefore it is 41.57 into 10 to the power minus 3 cubic meters. Equals to numbers of moles. Here the mass is given, no? So since the mass is given, we have to convert mass into moles. Right. We know that numbers of moles equals to mass divided by the molar mass. So I'm going to rearrange this equation as PV equals M over N times RT. So pressure equals to MVRT divided by capital T. Now the pressure equals to mass is 200 grams. That means 200 into 10 to the power minus 3 kilograms into volume is 41.57 into 10 to the power minus 3 cubic meters. R is 8.314. joules per mole per Kelvin. Temperature is 300 divided by molar mass of argon, that is 40 grams per mole. That means 40 into 10 to the power minus 3 kilograms per mole. Right. So we can simplify this. 10 to the power 3 to 10 to the power 3 gets cancelled off. 40 times 1, 40 times 5, right? To 200. Then here it is 5 into 41.57 into 10 to the power minus 3 into, I have given that 8.314 into 3 as 25. I have asked you to take it as 25. Why is that? 8.314 into 3 is 24.942. So we can approximately take it as 25. Sorry?
We should be divide them in
MRT over MB, no? Yes. Sorry. That's my mistake. Then 41.57 has to be counted. Yes. It should be over here. Then the answer will be 5 into. Okay. Now 8.314 times 5 is 41.57. Right. That means we can simplify it because 4.157 times 2 is 8.314. So we can cancel 8.314 times 1 times 5. Then 5 to this 5 gets cancelled. Then the final answer will be 300 divided by 10 to the power minus 3. So once it comes out, answer will be 3 into 10 to the power 5. That is the answer. 3 into 10 to the power. Did you get the answer? No? Why is that? ATM. That's this. 41.57 people on study. Was explained capabilities. Right. So those are the first 3 questions of that question. So let's come to the next situation. Right. So you can write down the next part of the question. Now, the valve P, the valve P is open. Now the valve P is open without changing the temperatures inside the bulbs. Without changing the temperature inside the bulbs.
We are going to write these numbers, 3 numbers as the products of the company.
Now the valve is open without changing the temperature. Next question is simple D. Simple D. What is the pressure inside? What is the pressure inside X? Actually, it's a new pressure. What is the new pressure in X? Then part E, next question. What are the partial pressures of helium and nitrogen? What are the partial pressures of helium and nitrogen? Then other one, in which direction does the gas diffuse once the valve is open? Yes. Right. In which direction the gas is diffused once the valve is open? Those are the next three questions. Quickly answer them. I'll give you about 5 minutes. Yes. Now see, now the valve P is open. So what has happened once the valve P is open, what will happen? Yeah, the X and Y will get mixed. What will happen to the temperature? Yeah, temperature remains the same because it says temperature is kept constant. Then what will happen to the volume? What the volume? It's been increased. Now both X and Y are being connected with each other. So the total volume is increased. Then what will happen to the pressure? We don't know whether it increase or increase. Anyhow, the pressure will be changed. So then, does the numbers of gas moles change? No, it's fixed. No, helium is there, nitrogen is there. Those values are fixed. If so, what are the only changes that take place? Pressure and volume. So if pressure and volume are the things which are not changing, what is the law that we can use? Yeah, V1 equals V2 V2. That law is called the Boyle law. Yeah, that's it. You can consider one gas and you can apply Boyle. What's the thing that we need to find out?
New pressure.
What is the new pressure in X? Initial pressure we know. Initial volume we know. Final volume we know. Finally, we can make a first. Like not all nervous system like a not volume. Volume of the country. Did you get it? I was thinking of a method to explain.
Really, she will take kids from our class and mistake.
I have been told that any region in the equation is required. It's as in this. So in A is yes, because in chemistry you are given marks to the value plus units.
Is it the same question?
Sorry.
What's the answer to the question? English.
Right. So in physics, it's not required to substitute all the units, but in chemistry, it's required. Huh? Not everywhere when substituting the variables, it's required because marks will be given for units as well.
So I'll ask the same question.
Yeah. Okay. The new pressure inside the bulb X that will be 2.9 into 12. Actually, there are two ways to find this. What is the temperature that we are going to keep bulb X? Is it 300? 300. 300. Now we bulb by the temperature is 400. Then it's not fair to use the boiler because temperatures are different. Okay, so let's do this one. It's like this. Now here we open the valve P. What will happen once we open the valve P? There will be mixing of the gases, helium and nitrogen with each other. That mixing takes place by flowing the gases here and there. But we know that gases that are under high pressure will flow towards the low pressure direction. So what is the high pressure over here? Here we have 2 into 10 to the power 4. Here we have 6 into 10 to the power 4. So where's the pressure that is higher? In X. So let's assume that the gas will be flowing from X to Y. That's just an assumption. Now we don't know whether it is exactly that. Right. Now initially we had 40 moles of helium over here. Out of that 40 moles, let's assume simple A moles or simple N moles are flowing from helium to nitrogen direction. That is from X to Y because of the high pressure inside there. Then if simple A moles of helium is flowing from X to Y, here the numbers of moles will be increased. Okay, but the most important thing is the pressures inside X and Y are equal to each other. Why is that? Because the whole system is now one system. Since the valve is open, X and Y are interconnected with each other, so the pressure is constant. Pressure is the same. Did you understand it? Now it's like this. Now here inside this room we have a particular pressure. Outside this room, in the next room also there's a pressure. Since these two rooms are connected with each other, the total pressure is not the total pressure. The pressures inside the two rooms are the same. Is it clear? Like But there are holes. There are doors and there are some gaps. This is not isolated. If it is isolated, it is right. So let's assume that, and then we can make the sum in that manner. Yeah, that's what we are going to do now. That's the thing that we had to find. See, pressure inside X. We know that pressure inside X equals to pressure inside Y as well. Right. Now here we have parts that are connected with each other. Right. So this is X and this is Y. Now initially we had 40 moles of helium. Right. So now due to the pressure change, let's assume that out of that 40, 80 moles are being transferred into that side. Now we have only 40 minus A in X. Then what will happen to the numbers of moles in Y? What is the initial numbers of moles in Y? I think we found it as 50. 50, no? So initially we had 50. Then A amount has been added into this. Did you understand that? So the total numbers of moles are like that. Sorry? In the previous calculations, I think we found. What is the mass of N2 is 1 So when finding it, we found it. That is, we can apply ED% RT and the N will be coming as 50. Actually, we found the mass as 1.4. Is it 1.4? 1.4 kilograms. If we divide it by the molar mass of N, then it will give us 50. Right. Any problem? Arjuna? Did you understand? Yes. It is here the negative So we are assuming only that flow. Okay, we are just making some. Now here we assume that here in this side we have high pressure. Right. Here we have 6 into 10 to the power of high pressure and here we have low pressure. So but we barrel open high to low pressure. We assume that. So initially we had 40 and from 40 A is being moved to this side. So that now the balanced ones will be 40 minus A. This will be 50 plus A. We don't know whether the gas moves from Y to X. Y to X. Yeah, the value for A will be a negative value. One of us simplify value. Right. So this is the thing happening. Then the temperatures are here it is 300, here it is 400 because the temperatures are kept without changing. Without changing. 300 Kelvin and inside this one is 400 Kelvin. Pressure will be P and here also P because the pressures are the same because it's the same system. Got it? Right. So then let's apply these values. Then to the bulb X we can apply P equals nRT. We can apply P equals nRT. We don't know the P. And the volume is 1.6628. Numbers of moles will be 40 minus A. R is 8.314. and the temperature is 300. Right. So this is for bulb X. Is it clear? Then we can subject P. That is 40 minus A into 8.314 into 300 divided by 1.6628. Let's take that as equation number 1. Then for the bulb white, again we can apply P equals nRT. Then their pressure will be numbers of moles, that is 50 plus A. R is 8.314. Temperature is 400. Divided by the volume there is 8.31. That is equation number 2. Right. Since both the pressures are equal, we can equalize these two. 1 equals to 2. They are 40 minus A into 8.314 into 300 divided by 1.6628 equals to 50 plus A into 8.314 into 400 divided by 8.31. So we can simplify and get a value for it. So that's up to you. Okay. I have done the chemistry part, the maths part is for you. Right, 8.314 to 8.314 gets cancelled out. 1 times 5 is there. Then 400, 2 zeros are being cancelled off. 5 times 3 is 50, 50 divided by 4. Likewise, once you simplify, you will get the value for A as 80 divided by 3.8. Right. So that means for A, the positive value is given. 80 divided by 3.8. So now it is confirmed that the gas is flowed from X to Y. Is it clear? The gas is flowing from X to Y. So that is A. We can find the value for A, but you have to find out the new pressure inside X. Then to the bulb X, we can apply ideal gas equation. Now we know the value of A, that is 8 divided by 3. Then we can simplify this equation and find the value for B. Then not that. Fine, that's a small small.
And limitation. We are working. So now it's clear that now I'm planning how the shop wishing we drew another person, you know, that we can be the is given them given that his market. Ayala, I don't get passes for him. Should pass for him. So I don't know. I like my function. Okay, now I you're gonna know. Yeah. There must see a lot of students on the violin activity. Our class. No, like there are no video students. I mean, either working so hard or not working.
60 minutes are there.
Yeah.
Payments now.
Yeah, yeah.
Chemistry, physics, that's all. Just gone crazy now. They got really gone.
He was so good.
No, it's just.
And so because when you had to win and they sounds funny.
Now, it's perfect. I'm gonna
It means very humble. And someone found you was going to be considered as
Boys in the certain doing.
So, benefiting the Chinese as and now data, like and use the t-shirt. Probably because now it's here. I would picture you never. I'm going to say, you know, you got the same video. Oh, we just carry it.
So yeah, I found it rather than my
And what you make the sound?
I forgot to be the sales phrase. I still remember this one. No. This one you put here and like that. I said, I'm not here of a class area when now in this electrics.
Right, so then we can apply this A to the ideal gas equation P equals nRT and find the value for P. Then for it, you can apply P equals nRT. Pressure equals to pressure into volume, that is 1.6628. Substitute the unit. I am not substituting because I am the sir. I am not going to write A level again. I don't need to write A level again. Those are the privileges. Right. So the N will be 40 minus A. So 40 minus A is 80 divided by 3.8. Into 8.314 into now the temperature inside the vessel X is 300. Right. You can simplify and you will get the answer for P as 2.90 into 10 to the power 4. That's it. Right, so that's the total pressure inside the vessel X. Now you are supposed to find the partial pressures of helium and nitrogen. Partial pressures of helium and nitrogen. partial pressure of nitrogen equals to mole fraction of nitrogen into total pressure. That is the equation. No? So mole fraction of nitrogen means numbers of moles of nitrogen divided by the total numbers of moles in N2 plus in helium into total pressure. So numbers of moles of nitrogen is 50, no? 50 divided by N2 is 50, helium is 40. Into total pressure is 2.90 into 10 to the power 4. So the answer will be 50 divided by 90 into 2.90 into 10 to the power 4. Then you can simplify this and get the value. You get the value as 1.288. Into 10 to the power 4. That is the partial pressure of N2. Then you have to find out the partial pressure of helium. That is total pressure minus partial pressure of N2. Then you can subtract 1.288 into 10 to the power 4 from 2.90 into 10 to the power 4. Here now. Okay, then here, in which direction the gas is diffused once the valve is open? Is it from X to Y or Y to X? X to Y. Now we found that 80 divided by 3.8 moles of gas has been diffused from X to Y. So the direction of the flow of the gas is from X to Y. Sorry. The value for 80 divided by 3.
Then you got nobody got the.
But if I was calculated.
26.667. They have more than 40 in the class. But if anything, okay, so let's start. Right. So now we have completed 4 units and this is the 5th unit. Energy. In here, now listen, we are not going to write today. I'll just explain you what energetic. So in energetics, we talked about the energy parameters in a chemical reaction. Right. Now we know that the chemical reactions take place due to their chemical activity. So for some chemical reactions, in order to take place, then we have to heat them. We have to heat the mix. Have you experienced that? We have to heat the mix. So once it's heated only, the reaction is start. Okay. So such reactions are called endothermic reactions. Endothermic, that means they are absorbing heat. During some reactions, energy is given out, that means heat is given out. Those reactions are called exothermic reactions. Remember that during the reaction gives away heat, that is exothermic. As that heat is given away, the system will get heat. Okay. Then there are some reactions which will absorb heat from surrounding for the reaction. We call them endothermic. Then the system will get cooled because the heat in the system is absorbed by the reaction mixture. Got it? Right. So those are the two main types of reactions. So, heat transfer that are different. For example, we have a hot object and a cold. Then heat will flow from hot to cold. Okay. So that is the form of transferring energy. Energy will be transferred from hot object to the cold object. Then the study about the heat transfer is called the thermochemistry. We call it thermochemistry. That is a study about the heat transfer. Okay. Then in this chapter, in this unit, we are going to learn about those heat transfer. We are going to learn about the heat energy transfer. That's from hot object to cold object. So that is being specified under this thermochemistry. Then if we talk about the thermochemistry, there are some terms that we should know. One thing is system. The system is anything that we consider where the reaction takes. So this is the system. Outside the system, we have the surrounding. Then the system is separated from the surrounding by the boundary. So this is called the boundary. boundary separates the system from the surrounding. If we talk the systems, there are three different types of systems. Open system, closed system, and isolated. Those are the three types of systems. So in an open system, both energy and matter can be transferred. Energy as well as matter is transferred. For example, let's say the hot water heater. This is the open system. Why is that? Because it is hot. Then heat will be given out from the hot from the hot system to the surrounding. As well as we know that once it is hot water heater, we can see the steam is coming out. Steam means water vapor. So water is the matter, right? Then energy is moved as heat. So that is called an open system. Then in a closed system, energy is transferred, but not the matter. Matter is heat. For example, a closed water bottle, hot water bottle. So water inside is here inside this one we have water. It is hot. Only the heat energy is being coming out as radiation of thermal heat, but the matter is remaining inside this without heat. Then in isolated system, both matter and energy get in system. It's not in. For example, we can do a thermal. So we can give a thermal. What is thermal? Sorry. Yeah, if time means not instantaneous, after about 24 hours, some of the heat is very similar, but not so long. It is not perfect in terms of. We know that the matter is preserved, that matter is there, it's not being vaporized, and the heat is also preserved. So those are the three types of systems that we use. Then if we consider these systems, there are systems can be again divided into two types as homogeneous and heterogeneous. What are homogeneous systems? Homogeneous systems, like all the matter are in the same physical. That means if it is a liquid, if it is a gas, gas. So in homogeneous systems, we cannot distinguish between the compositions that we cannot distinguish the matter. Then in heterogeneous ones, the components are in different systems. That means, for example, a mixture of sand and water. We can easily sand particles and water. So those are the heterogeneous. Then we talk about the properties of the system. There are two main types of properties that are microscopic properties and macroscopic. Microscopic properties, they are associated with the atomic scale. And the macroscopic properties, they are associated with the bulk scale. For example, the pressure, volume, temperature, density, concentration, surface area, surface tension, refractive index, likewise, those are macroscopic properties that they are related to the bulk. Then the speed of a molecule, kinetic energy, likewise, those are microscopic. That is, they are at the molecular level of that. Then again, macroscopic properties are subdivided into two categories as extensive properties and intensive properties. The properties that depend on the amount are called extensive. Properties that depend on the amount of are called extensive. For example, volume. We know that once the amount increases, volume increases. Weight is an extensive property. Then volume, weight, then mass, then energy. Energy is also extensive. Depends on the mass of the particle. Depends on the amount of. Then the intensive properties, they do not depend on the amount. For example, density does not depend on the volume or the mass or the amount. Because if you consider 1 milliliter of water, from example, that is having a density. If you consider 1000 milliliters of water, it's also having the same density. No? So it doesn't depend on the size. So those are the key terms that you should know about this. So if you are talking further about this, we are talking about the enthalpy. That is the most important part in this test. So enthalpy is that is used to quantify the heat flow into or out of the system. Now we learned that there's a system from the system, it can be given out or it can be thrown in. To quantify that, we use a parameter called enthalpy. So enthalpy is not clearly energy. There's a difference between energy and enthalpy. So this is a parameter to quantify. So it is symbolized by the symbol symbolized. And there are 14 enthalpies we need to learn. Okay. Yes. The energy diagrams and reaction profiles are there. Reaction profiles, thermochemical cycles, and example, what are the processes? One thing is formation. During the formation of certain substance, there will be heat energy. That is called formation. Then during a combustion reaction, the combustion. During acid-base reaction, we call it neutralization because the process is a neutralization. Then atomization, sublimation, vaporization, dissolution, evaporation. Then what else? Fusion, ionization, liquid chemistry, all those. So that will be discussed next week. So this will be the end of the class.